On March the 4th, 2018, a 76-year-old man by the name of Stephen Hawking uploaded a revised manuscript for review. He died 10 days later. The paper was the last thing he worked on in his life. After his death, newspapers around the world ran the same headline: Stephen Hawking's final paper proves the multiverse exists. The headlines were wrong in exactly the way that mattered. What Hawking and his co-author submitted was not a defense of the infinite multiverse. It was an attempt to kill it. This is a video about the document he was working on when he ran out of time. The paper was titled, "A Smooth Exit from Eternal Inflation." His co-author was Thomas Hertog, a Belgian cosmologist at KU Leuven who had worked with Hawking for 2 decades. For most of the past 40 years, cosmologists had treated the multiverse as a feature, not a bug. The idea had quietly become part of the foundation. An eternal multiverse. Infinite realities with infinite histories. It explained why the constants of physics seem so finely tuned for the existence of stars and planets. It explained the strange smoothness of the cosmic microwave background. The multiverse, in other words, was load-bearing. Take it away, and a great deal of modern cosmology gets a lot harder to hold up. Hawking spent the last 20 years trying to dismantle it, not proving the multiverse exists, limiting it, containing it, dragging infinity back inside the boundaries of testable science. Hawking had been told at 21 that he had 2 years to live. He had lived 55. He had spent that half-century learning to be skeptical of infinities. There is something the popular telling of this story almost always skips. In his final months, Hawking was not trying to make the universe larger. He was trying to make it smaller. He wanted to take the runaway infinity that cosmology had grown comfortable with and force it back inside borders that science could actually test. There is a phrase you will hear several times over the course of this evening. The phrase is the smooth exit. It is the title Hawking and Hertog gave to their paper, and it is the technical name for the mechanism they were trying to install at the boundary between eternal inflation and the universe we actually inhabit. That is the recurring thread of this story. At first, it will sound technical. By the end, it will sound unsettling. Because hidden inside that phrase is a problem that has haunted cosmology for decades. If eternal inflation never truly ends, then physics loses the ability to predict anything at all. The paper was published in the Journal of High Energy Physics 6 weeks after Hawking's death. It has been cited several hundred times since. The man who co-wrote it never saw a single one of those citations. If the unanswered questions of the universe keep you company at night, you are in the right place. Subscribe and settle in. The paper he submitted 10 days before he died was the closest he ever got. We will get to exactly why a Nobel laureate at MIT called it heavy on speculative assumptions, and why a Belgian cosmologist in Leuven has spent the years since trying to prove the critics wrong. To understand why this paper matters, you have to understand what the multiverse was supposed to be. Not the multiverse of pop science books and Marvel films. The multiverse cosmologists actually mean when they use the word, the one that emerged, slowly and almost by accident, out of a single theoretical fix proposed by a young physicist at Stanford in the autumn of 1979. His name was Alan Guth. He was 32 years old, a postdoctoral fellow at the Stanford Linear Accelerator Center on a contract that was about to run out. Not famous, not even tenured. Trained as a particle physicist, working in cosmology only because the jobs in his own field had dried up and the cosmology problems happened to interest him. The problem he was thinking about in the early hours of December 6, 1979, by his own later account, was a deep inconsistency in the standard Big Bang model. The model worked beautifully at later times, but pushed back to the first fraction of a second, it required absurd fine-tuning of the initial conditions to produce a universe that looked anything like the one we live in. Two specific inconsistencies bothered him most. The first was called the flatness problem. The geometry of the observable universe is, as far as anyone can measure, almost perfectly flat, meaning that two parallel light beams sent in opposite directions stay parallel forever, neither converging nor diverging. In the standard Big Bang model, this flatness was not natural. It required the early universe to have a density of matter and energy tuned to within 1 part in 10 to the 60th power of a specific critical value. Any deviation, and the universe would have either collapsed back on itself in the first second or expanded so fast that no galaxies could ever form. The observed flatness was a knife edge that the Big Bang had no obvious reason to balance on. The second was called the horizon problem. When astronomers measure the cosmic microwave background, the leftover radiation from the moment the universe became transparent, 380,000 years after the Big Bang, they find that the temperature is almost identical in every direction. About 2.7 Kelvin across the entire sky, with deviations of only 1 part in 100,000. But two patches of sky on opposite sides of the heavens are too far apart for light to have ever traveled between them in the lifetime of the universe. They have never been in causal contact. They could never have exchanged energy and reached the same temperature. And yet they have. By every measurement we have ever made of them, they have. The standard Big Bang model offered no answer to either problem. Both required the initial conditions of the universe to be set, by hand, to extremely specific values with no underlying reason. Guth was not the first physicist to notice this. He was the first to propose a mechanism that fixed both problems at once. The fix was inflation. The idea was simple in concept and shocking in scale. In the first 10 to the negative 36 seconds of the universe's existence, space itself underwent a brief, exponential expansion. Not the gentle expansion described by Hubble, an expansion in which every cubic centimeter of space doubled in size every 10 to the negative 35 seconds, doubling at least 60 times in total. By the end of the inflationary epoch, a region the size of a proton had been stretched into something larger than the observable universe today. The flatness problem disappeared because any curvature was diluted away by the expansion. The horizon problem disappeared because every part of the observable universe had once been close enough to touch. Guth published his paper, titled Inflationary Universe, in the journal Physical Review D in January of 1981. The paper was almost immediately recognized as one of the most important contributions to cosmology in 50 years. Within a few years, the basic framework of inflation had been adopted by most of the cosmology community. The match between inflation's predictions and the temperature pattern of the cosmic microwave background, measured first by the COBE satellite in 1992 and refined by the Planck mission 2 decades later, became one of the strongest pieces of evidence in modern cosmology that the early universe had really inflated. The Nobel Committee has never given inflation the prize. Among working cosmologists, Guth's idea is treated as effectively confirmed. There was, however, a problem. Guth's original proposal had a flaw. His version of inflation, which he later called old inflation, required the false vacuum state, the high-energy condition that drove the exponential expansion, to decay through a process of bubble nucleation, similar to how a supercooled liquid suddenly freezes into ice. The trouble was that the bubbles never collided. They grew too slowly, and the space between them inflated too fast. The result was not a smooth, hot, homogeneous early universe of the kind we actually observe. It was a sparse archipelago of bubble universes, separated by inflating space, never meeting. Guth himself acknowledged this in the conclusion of his 1981 paper. He called it the graceful exit problem. The mechanism for ending inflation gracefully, for transitioning from the exponentially expanding false vacuum to the slowly expanding hot Big Bang we live in, did not work. The solution came from another young physicist working in Moscow in 1982. His name was Andrei Linde. Linde proposed a variant called new inflation, in which the false vacuum decay happened not by bubble nucleation, but by a slow rolling of the inflaton field down a gentle potential. In new inflation, the entire observable universe came out of a single bubble, smoothly expanding and reheating into the hot Big Bang. The graceful exit problem appeared to be solved. Then, in 1983, Linde proposed an even more general version, which he called chaotic inflation. In chaotic inflation, the inflaton field did not start in any particular state. It started everywhere, in random configurations. In most regions, the field was too low or too uneven for inflation to ever begin. But in some regions, vanishingly rare across an infinite expanse of spacetime, the field happened to be high enough and smooth enough for inflation to begin. Those regions inflated. The rest did not. And the inflating regions kept inflating, expanding exponentially, while quantum fluctuations within them continually produced new subregions where inflation continued, and others where it stopped. This was the moment the multiverse appeared. The argument was first laid out cleanly by Paul Steinhardt, then at the University of Pennsylvania, in a paper presented at a conference in October of 1983. Steinhardt showed that even within new inflation, the process of false vacuum decay was statistical. The decay never finished everywhere at once. In any region where it had not yet finished, inflation continued. And because inflating regions grew exponentially faster than the rate at which they decayed, the total volume of inflating space increased without bound, forever. A few years later, Alexander Vilenkin, a Ukrainian-born physicist working at Tufts University outside Boston, showed that this was not a quirk of new inflation. It was generic. Almost any model of inflation, taken seriously, produced eternal inflation as an output. Once inflation started in any region of the universe, it never globally stopped. It only locally stopped, in patches, while the surrounding space continued to inflate at an exponentially accelerating rate. By the mid-1980s, this picture had become widely accepted within the inflationary cosmology community. Linde formalized it in a paper in 1986, where he gave it the name eternal chaotic inflation. The early universe in this picture was not a single event. It was an ongoing process. A single chaotic inflating region, somewhere in the deep past, gave rise to an infinite, self-reproducing fractal of bubble universes. Each bubble was a region where inflation had locally ended, and a hot Big Bang had begun. Each bubble contained in principle its own observable universe. Most bubbles were sterile, with physical laws too hostile for chemistry. Some bubbles, fewer than one in some astronomically large number, happened to have the right balance of constants for stars and planets to form. We live in one of those bubbles. That was the multiverse, not the entertaining one of science fiction, the cosmological one, a vast, possibly infinite collection of pocket universes, embedded inside an eternally inflating sea, each with potentially different physical laws, almost all of them unreachable across distances that grow faster than any signal could ever cross. For a while, this was treated by most working cosmologists as a curiosity, an interesting mathematical consequence of inflation, but not something anyone was supposed to take literally. Then, in 2003, a Stanford physicist named Leonard Susskind published a paper that changed the consensus. The paper drew on string theory, the leading candidate for a unified theory of quantum gravity. String theory, by the early 2000s, was understood to have not one solution, but an enormous number of them. Different ways of compactifying the extra dimensions of space produce different effective physics in the resulting four-dimensional universe. Different values of the cosmological constant, different particle masses. The number of distinct string theory vacua, by the most common estimate, sits somewhere around 10 to the 500th power. Susskind argued that eternal inflation provided exactly the mechanism needed to populate this enormous space of solutions. Each pocket universe produced by eternal inflation would, on cooling, settle into one of those vacuum states. With 10 to the 500th power options available and an infinite number of pocket universes being produced forever, every possible configuration would be realized somewhere. And the constants of physics in any given pocket, including the ones we measure in our own, would be set, effectively, at random. This was the moment the multiverse became load-bearing. The reason was the anthropic principle. The principle had been stated explicitly in 1973 by the Australian physicist Brandon Carter at a conference in Krakow celebrating the 500th anniversary of the birth of Copernicus. It came in two forms: a weak form, which is essentially uncontroversial, and a strong form, which is. The weak form says simply that the observed values of the physical constants are not random samples from all possible values. They are samples from the set of values compatible with the existence of observers like us. We could not observe a universe where carbon could not form. So when we look around and see a universe where carbon does form, we should not be surprised. We are looking from a position that filters out everything else. By itself, the weak anthropic principle does not explain why the constants have the values they do. It only says that, given those values are what they are, we should not be shocked to find ourselves in a universe shaped by them. The explanation comes from combining the principle with the multiverse. If there are many universes, with the constants of physics taking different values in each, then the existence of a universe with our specific constants is not a fine-tuned coincidence, it is a statistical certainty. Out of the infinite ensemble, some universes will have the right physics for observers to exist, and those are, by definition, the universes from which the question can be asked. The argument was attractive to many physicists for the same reason it was suspicious to others. It explained things. Steven Weinberg, the Nobel laureate at the University of Texas, had used a version of it in 1987 to predict, correctly, that the cosmological constant should be small but non-zero, an estimate later confirmed by the discovery of dark energy in 1998. Andrei Linde, by the late 1990s, was openly defending the multiverse as a serious physical hypothesis. Susskind's 2003 paper, building on these earlier currents, made the position mainstream. The combination of eternal inflation, string theory, and the anthropic principle was, by the mid-2000s, the working framework of much of theoretical cosmology. And then, very quietly, the problem with it began to surface. The problem had a name. It was called the measure problem. It had been noticed, in various forms, by Vilenkin in the 1990s and by Linde himself in a series of papers across 2 decades. Guth had raised it independently in the early 2000s. The problem was this: if eternal inflation is correct, then there is not just an infinite ensemble of pocket universes. There is an infinite ensemble of every possible kind of pocket universe. Universes like ours. Some nothing like ours. Worlds in which the laws of physics fluctuate randomly from one region to the next. Pockets in which a Boltzmann brain spontaneously assembles itself out of vacuum noise and dissolves a moment later. All of them. Infinitely many of each. The measure problem is the question of how, in such an infinite ensemble, you assign probabilities to anything. In ordinary statistics, you count outcomes. The probability of an event is the number of times that event occurs divided by the total number of trials. But when both the number of events and the number of trials are infinite, that ratio is undefined. You can get any answer you want depending on the order in which you count. By the mid-2000s, the measure problem had become a recognized crisis at the foundations of inflationary cosmology. Multiple competing methods for assigning probabilities, the proper time cutoff, the scale factor cutoff, the causal patch measure, the watcher measure, were each producing different predictions. Some methods predicted that you should overwhelmingly expect to find yourself in a universe much younger than this one. This was called the youngness paradox. Others predicted that the vast majority of observers in the multiverse should be Boltzmann brains, briefly self-assembling out of thermal noise. None of the methods agreed on what the multiverse, taken seriously, should actually look like. A theory that predicts everything predicts nothing. That was the criticism. By the early 2010s, it had become the central technical concern about eternal inflation among physicists who took the framework seriously enough to worry about its consequences. It was also the loose thread Hawking spent the last decades of his life trying to pull. There was a single persistent loose thread: infinity. Eternal inflation predicted an infinite multiverse, and the mathematical foundation of eternal inflation rested on a particular assumption that quantum mechanics could be treated as small fluctuations on top of a classical, smoothly expanding background, with general relativity governing the background and ordinary quantum field theory governing the fluctuations. This was the standard recipe of modern cosmology. It had been working successfully for decades. It was the recipe used to predict the temperature variations in the cosmic microwave background. It was the same recipe behind models of galaxy formation. In almost every other context, it behaved itself. But eternal inflation broke it. The reason was structural. In eternal inflation, the quantum fluctuations were not small. They were the thing that drove the whole picture. In regions where inflation continued, quantum fluctuations were what made the inflaton field rare enough and smooth enough in some subregions for inflation to keep going. Those rare quantum events were not perturbations on top of a classical background. They were what determined which classical background you ended up with. The clean separation between classical geometry and quantum fluctuation that the rest of cosmology relied on, the separation that made every other prediction tractable, did not survive contact with eternal inflation. Hertog put it bluntly in interviews after Hawking's death: the dynamics of eternal inflation wipes out the distinction between the classical and the quantum. The math the theory uses to predict the multiverse breaks down in the exact regime where the multiverse is supposed to be produced. The theory eats its own foundation. Stephen Hawking had been suspicious of infinities in cosmology for almost his entire career. The suspicion went back further than the multiverse problem. It went back, in a sense, to 1974, when Hawking made the discovery that defined the first half of his career. The discovery that black holes are not, after all, perfectly black. The discovery emerged from a calculation Hawking was doing on the boundary between general relativity and quantum mechanics. Specifically, he was working out what quantum field theory looks like in the curved spacetime near the event horizon of a black hole. The standard understanding, before Hawking's calculation, was that black holes were absorbers. Anything that crossed the event horizon was lost forever. Nothing came out. Hawking, applying the techniques of quantum field theory to this problem, found something different. Quantum mechanics, near an event horizon, allows pairs of virtual particles to spontaneously appear out of vacuum. One with positive energy, one with negative. In ordinary empty space, the pair annihilates almost immediately, and the energy ledger is restored. Near a black hole horizon, however, one particle can fall through the horizon while the other escapes outward. The escaping particle, viewed from far away, looks like radiation emitted by the black hole. The black hole itself, viewed from far away, looks like it is slowly losing mass to this radiation. The calculation took Hawking the better part of 2 years to complete and publish. The paper, titled "Particle Creation by Black Holes," appeared in the journal Communications in Mathematical Physics in 1975. It was recognized almost immediately as one of the most important results in theoretical physics in a generation. It connected the structure of general relativity with the principles of quantum mechanics in a calculation that also made unavoidable contact with thermodynamics. Black holes, Hawking had shown, were not just gravitational objects. They were thermodynamic objects. They had a temperature. They had an entropy. They radiated. The entropy was the part that mattered for what came later. The entropy of a black hole, according to Hawking's calculation, and an earlier closely related argument by the Israeli-American physicist Jacob Bekenstein, was proportional to the area of the event horizon, not to the volume of the interior. This was a deeply strange result. Entropy, in every other context, scales with volume. The entropy of a glass of water depends on how much water is in the glass, not on the surface area of the glass. The entropy of a black hole, alone among all thermodynamic systems anyone had ever studied, scaled with the surface area of its boundary. Hawking and Bekenstein arrived at the area scaling independently, and both were initially puzzled by what it meant. The full physical interpretation that the area scaling reflects a deep principle about how information is encoded in gravitational systems, that the interior of a black hole is in some sense redundant with its boundary, would take another 2 decades to work out. The holographic principle of Hooft and Susskind in the early 1990s and the Mulder-Sina correspondence of 1997 were the eventual answer. The interior of a gravitational system in the holographic picture is fully described by the data on its boundary. Volume is a kind of illusion. Surface is where the real information lives. Hawking had been there from the beginning of this whole line of thought. He was the one who first wrote down the formula for black hole entropy. He was also the first to notice that gravity, when made quantum, seemed to want to live on boundaries rather than in volumes. He spent the rest of his career, in one way or another, working out what this meant. The smooth exit paper was, in this sense, not a departure from his earlier work. It was a continuation of it. The same boundary counting argument that gave a black hole its entropy in 1974 was, in 2017, being applied to eternal inflation. The same principle, that the interior of a gravitational system is encoded by data on its boundary, with the entropy bounded by the area, was being extended from black holes to cosmology. The 43 years between the two papers were, by Hawking's own description in interviews, a single intellectual arc. This is also why he was so resistant to the infinite multiverse. He had spent his career arguing that gravitational systems, properly understood, are bounded. Their information content is finite. Their entropy is computable. The eternal inflation multiverse violated all of this. It claimed an infinite ensemble of universes with no boundary, no entropy bound, no way to count. To Hawking, this was not just a mathematical inconvenience. It was a betrayal of the principle his life's work had been built on. The Vatican proposal in 1981, the no-boundary collaboration with Hartley in 1983, the decades of refinement that followed, and the smooth exit paper at the end of his life, all of these were, in Hawking's mind, the same project. The project of taking the boundary principle seriously enough to apply it to the universe as a whole. It went back, by his own account, to October of 1981. The Pontifical Academy of Sciences, the scientific body of the Vatican, had organized a conference in Rome on cosmology and the philosophy of science. Hawking was invited, along with most of the leading theoretical physicists of the day. He was 39 years old and already established as one of the most important young theorists in his field. He gave a talk at the conference about the boundary conditions of the universe, the question of what determines the initial state of the cosmos at the moment of the Big Bang. The talk floated an idea Hawking had been circling for some time. What if the universe had no boundary at all? What if the Big Bang, conceptually, was not a singular point at the beginning of time, but rather a kind of geometric pole, like the North Pole on a globe? The pole is finite. It is the boundary of all the latitude lines on the planet. But it is not a boundary in the sense of an edge. It is not a place where the surface ends. There is simply no further north to go. North runs out, smoothly, without anything happening at the point itself. Hawking suggested the early universe might be similar. Time in the standard Big Bang model ran backward to a singular point, a moment where the equations broke down and the laws of physics had no further reach. Hawking proposed that this picture was wrong. Time, traced backward, did not hit a singularity. It smoothly curved into a finite, regular geometry with no boundary at all. The question of what happened before the Big Bang in this picture was as meaningless as the question of what was north of the North Pole. The Vatican audience, by accounts of the meeting, was unsure what to make of it. The Pope at the time, John Paul II, gave a closing address, suggesting that the moment of the Big Bang itself was beyond the reach of science and should be left to theology. Hawking did not respond to this directly, but he later wrote that he was relieved the Pope had not asked him about the no-boundary idea, because if he had, Hawking would have had to point out that the picture seemed to dispense with the need for a beginning at all. The Vatican proposal was, at that point, a sketch. It needed mathematical machinery to back it up. Hawking found that machinery at a summer workshop at the Institute for Theoretical Physics at the University of California, Santa Barbara, in the summer of 1983. The workshop brought together cosmologists and quantum field theorists for several weeks of focused collaboration on the early universe. One of the resident theorists at UC Santa Barbara was an American physicist named James Hartle, an expert in the foundations of quantum mechanics and the application of path integral methods to gravity. The path integral, originally developed by Richard Feynman in the late 1940s for ordinary quantum mechanics, is a way of computing the probability of a quantum system going from one state to another by summing over every possible history that connects them. Each history contributes a complex weight, and the weights are added together to give the total amplitude. Hartley had been thinking about how to apply this technique to the universe itself. The technical challenge was that the path integral for gravity, in its ordinary form, does not converge. The sum over histories grows uncontrollably. To make it converge, you have to rotate the time coordinate in a specific way, sending it through what mathematicians call imaginary time. In imaginary time, the geometry of space-time becomes Euclidean rather than Lorentzian, and the path integral becomes well-defined. Imaginary time sounds like a mathematical trick, but it has a precise physical meaning. In ordinary time, a quantum system that persists for a long interval contributes oscillating terms to the path integral, and those oscillations can cancel each other in awkward ways. In imaginary time, the oscillations turn into smooth, decaying exponentials, and the path integral converges to a definite answer. The procedure is used routinely in quantum field theory for calculations that would otherwise be intractable. Hartley's contribution was to show that the same procedure, applied to the gravitational degrees of freedom of the universe itself, could in principle define a well-behaved quantum state for the cosmos. Hawking arrived at Santa Barbara with the no-boundary idea. Hartley had the path integral machinery to make it precise. Over the 4 weeks of the workshop, they worked out the proposal in detail. The result was a paper titled Wave Function of the Universe, published in Physical Review D, Volume 28, in 1983. The paper proposed that the quantum state of the universe could be computed as a path integral over all compact Euclidean four-dimensional geometries with no boundary. The Big Bang in this picture was not a singularity. It was the point at which Euclidean time smoothly transitioned into Lorentzian time, and the universe began to behave classically. The proposal was elegant. It eliminated the need for arbitrary initial conditions. The state of the universe was not something to be set by hand at the moment of the Big Bang. It was determined, uniquely, by the requirement that the geometry have no boundary. The no-boundary proposal, as it came to be called, was a candidate solution to one of the deepest problems in cosmology, the problem of why the universe began the way it did. But the proposal had a difficulty. When Hawking and Hartley worked out what kind of universe the no-boundary proposal predicted, the answer was not quite what they hoped. The proposal predicted a universe that was smooth, homogeneous, and inflationary in the very early moments. That part was a success, but it also seemed to predict a universe that was overall empty, or close to it. A universe that inflated, but did not produce the rich structure of stars and galaxies that we actually observe. This was a serious problem. The whole point of cosmology is to predict the universe we observe, and a proposal that predicted the wrong universe was not, by the standards of the field, a successful theory. Some of Hawking's collaborators argued that the calculation must be incomplete, that quantum corrections, or stringy effects not yet understood, would eventually push the predicted universe towards something more like our own. Others, including Linde and Vilenkin, argued that the no-boundary proposal was simply wrong, and that a different choice of boundary condition for the universe, a tunneling wave function for instance, would give better predictions. The debate ran through most of the late 80s and the 90s. Hawking, for his part, defended the no-boundary state through every iteration of the argument. For most of the next 2 decades, the proposal sat in this awkward state. It was widely admired as a mathematical achievement. It was widely cited in the cosmology literature. It was almost universally regarded as not quite working, in the sense that it did not, by itself, reproduce the universe we live in. Hawking continued to work on it. He worked on it through the 80s and the 90s. He stayed with it after his speech was lost to motor neuron disease, dictating revisions through the cheek twitch interface that became his only remaining mode of communication. The no-boundary proposal was, for him, a 35-year unfinished project. The question of how to get it to predict the kind of universe we actually inhabit was the problem he could never quite solve. By the late 1990s, Hawking's disease had progressed to a point where collaboration of any kind required extraordinary patience. He had been diagnosed with motor neuron disease, what Americans call ALS, at the age of 21 in 1963. He had been told then that he had 2 years. In the decades since, his condition had progressed slowly but inexorably. He had lost the ability to walk in the 1960s and the ability to write in the 1970s. The pneumonia attack of 1985 had required a tracheotomy, and he had lost his voice. From that point forward, he communicated only through an electronic speech synthesizer, controlled at first by a handheld clicker, and later, as the disease consumed even that motor control, by a single muscle in his cheek. By the late 1990s, he could produce 1 to 2 words per minute. A typical research conversation, conducted at his pace, might last 6 hours. In the summer of 1998, a 23-year-old graduate student from Belgium walked into Hawking's office at Cambridge looking for a thesis project. His name was Thomas Hertog. He had been born in 1975 and had taken his master's degree in physics at the Catholic University of Leuven the previous year. He had been admitted to the doctoral program at the Department of Applied Mathematics and Theoretical Physics, DAMTP as it was known, and he had been told on his first day that Stephen Hawking was looking for new students. Hertog later described the meeting in detail in his 2023 book, On the Origin of Time. He had crept into Hawking's office on a hot summer afternoon. Hawking was in his motorized wheelchair, his head supported by the chair's brace. He spoke through the cheek-driven speech synthesizer that had been his only mode of communication since the tracheotomy. Hawking spent a long moment looking at Hertog without saying anything. Then he tapped the clicker against his cheek, and the synthesizer produced its first sentence. "The universe we observe appears designed." Hertog wrote later that he had not expected that to be the first thing Hawking would say. He had expected something about black holes, or about the technical details of whatever calculation Hawking was working on at the time. Instead, the most famous theoretical physicist in the world had opened the conversation by stating, calmly and directly, what most cosmologists privately thought but rarely said out loud, that the precise values of the physical constants seem astonishingly well suited to the existence of life, and that this fact demands an explanation. Hawking already had an idea what kind of explanation he wanted. The multiverse was not going to be it. Hertog's doctoral thesis, completed in 2001 and titled On the Origins of Cosmic Expansion, was the first major work of his career. It dealt with technical questions about how inflation could be embedded inside the no-boundary framework. The thesis was supervised by Hawking, with substantial input from Hartley, who flew in periodically from California. Hertog finished, was awarded the PhD, and then stayed in Cambridge as a postdoctoral researcher, continuing the collaboration. By the early 2000s, the three physicists were meeting regularly to push the no-boundary proposal further. Hartley, the senior figure, brought decades of work on the foundations of quantum mechanics. Hertog, the youngest, did much of the technical labor, the long calculations and the drafts that Hawking would revise word by word over weeks of dictation. The collaboration that began in that summer office meeting would last 20 years. The work was painstaking. The Hawking of 2000 could speak only by tapping a single button. The synthesizer added each word to a cue, and a complete sentence might take several minutes to produce. Hertog later said that the slow pace of conversation had a strange advantage. It forced every word to be deliberate. The collaboration developed its own grammar of facial expressions and head tilts, with Hertog reading nuance from movements that nobody outside the close circle could have interpreted. The mathematical work, through the early 2000s, focused on showing that the no-boundary proposal could predict a universe consistent with observation if combined with the right understanding of inflation. By the mid-2000s, Hawking, Hertog, and Hartley had begun publishing together on a more ambitious version of the no-boundary proposal, one that incorporated the enormous space of possible vacua predicted by string theory. They argued that the no-boundary state selected a specific subset of those vacua, rather than producing all of them at once. This was the seed of what they would later call the top-down approach. In standard cosmology, you reason from the bottom up. You start with initial conditions at the Big Bang, you apply the laws of physics, and you compute what universe you get. In top-down cosmology, you reason from the present backward. You start with the fact of observers like us, and you compute the quantum amplitude for the histories that could have produced us. The two approaches give different answers because of an old feature of quantum mechanics. The observer affects what is observed, even retrospectively. Hawking and Hertog were arguing that this feature, when applied to the universe as a whole, dramatically constrains the kinds of cosmic history the no-boundary proposal can predict. The intuitive version of the argument goes like this. Quantum mechanics does not predict what an electron is doing. It predicts the probability distribution of what an electron will be measured to be doing when a measurement is made. The wave function evolves smoothly, but the act of measurement selects, from an ensemble of possible histories, the specific history that is consistent with the observed outcome. Hawking and Hertog were extending this idea to cosmology itself. The history of the universe, in their framework, is not a single objective sequence of events. It is an ensemble of possible histories, weighted by the probability amplitudes that the no-boundary geometry assigns to each. The observers in those histories, including us, are doing the measuring. And the act of being observers, of being able to ask the question at all, selects the histories that are consistent with our existence. By 2011, after years of mathematical refinement, they had reached an insight that would set the direction of the rest of their work. The insight was that the no-boundary proposal, properly formulated, did not select a unique universe. It selected a specific, finite ensemble of histories, a small, structured slice through the vast space of possibilities offered by string theory, all of them compatible with observers. The multiverse, in this picture, was not infinite. It was bounded. If they were right, eternal inflation as a generator of an infinite fractal of pocket universes was simply wrong. The no-boundary proposal, properly extended, made the question of what kind of universe could exist after inflation finite. Answerable. Possibly even testable. They needed a name for this finite exit from inflation. The name they eventually chose was the smooth exit. By 2017, Hawking and Hertog had written up the first version of the paper that would carry that name. They submitted it to the archive, the preprint server physicists used to circulate drafts, on July 24th of that year. They knew the work was not finished. They knew the mathematical machinery was, by the standards of physics, preliminary, a toy model rather than a full theory. They submitted it anyway. They had a reason to hurry. The paper made a single, central, technical claim. They could show, using mathematics borrowed from string theory and quantum cosmology, that the exit from eternal inflation was not infinite. They could show that it was bounded. The question was whether the math actually worked. Hawking had less than 9 months to live. The paper Hawking uploaded to the archive on March 4th, 2018, was 23 pages long. The title, A Smooth Exit from Eternal Inflation, ended with a question mark. The question mark was deliberate. Hawking and Hertog were not claiming to have solved the problem of eternal inflation. They were claiming, more cautiously, to have shown that the problem might be solvable using a particular mathematical strategy borrowed from a different corner of theoretical physics. The strategy had been developed over 20 years to study black holes and quantum gravity. Applying it to cosmology was a stretch, but the alternative, accepting the infinite multiverse as the final word on the structure of reality, was not, by Hawking's standards, a satisfying place to leave physics. The strategy was holography. Holography, in the physics sense, is the principle that the information content of a region of spacetime can sometimes be fully described by a theory living on the boundary of that region. The idea first emerged in the early 1990s in the work of the Dutch theoretical physicist Gerard Hooft and the American physicist Leonard Susskind. They had been thinking about black holes, specifically about a strange result from the 1970s showing that the entropy of a black hole is proportional not to its volume, but to the area of its event horizon. The entropy of a black hole, in other words, scales as if the information inside the black hole were actually stored on the two-dimensional surface surrounding it. The interior was, in some precise sense, redundant. The boundary had everything. This was a hint at something deeper. The full development came in November of 1997, when the Argentine-American physicist Juan Maldacena published a paper showing that a specific kind of quantum gravity theory in a five-dimensional curved space was mathematically equivalent to a specific kind of quantum field theory in a four-dimensional flat space. The five-dimensional gravity theory and the four-dimensional field theory contained, in the technical sense, the same physics. Every quantity computable on one side could be computed on the other. The relationship became known as the AD-S/CFT correspondence, after the technical names of the two sides. Anti-de Sitter space on the gravity side, conformal field theory on the field theory side. These names need a little unpacking because they matter for what Hawking and Hertog tried to do. Anti-de Sitter space is a particular kind of curved geometry, a spacetime with constant negative curvature, of the sort that mathematicians study in differential geometry and physicists use as a controlled laboratory for quantum gravity. It has a clean asymptotic boundary, a kind of mathematical horizon at infinity, which is what makes the holographic correspondence work. Our universe, importantly, is not anti-de Sitter. It has positive curvature, technically of the kind described by de Sitter space, named after the Dutch astronomer Willem de Sitter, who first wrote down the solution in 1917. This asymmetry between the friendly anti-de Sitter case, where holography is well understood, and the awkward de Sitter case that actually applies to cosmology, is one of the central technical difficulties of applying holographic methods to the real universe. A conformal field theory is a quantum field theory with a particular kind of symmetry. The symmetry is scale invariance. The theory looks the same at every scale, from the very small to the very large, the way a fractal pattern looks the same at every magnification. Conformal field theories are particularly well understood mathematically. They appear across many areas of physics, from condensed matter to string theory, and the machinery for computing with them is highly developed. This was part of the attraction of Maldacena's correspondence. It mapped the difficult problem of quantum gravity in a higher dimension onto the relatively well-understood problem of a conformal field theory in a lower one. The Maldacena correspondence has been, in the 20-some years since its discovery, one of the most heavily studied results in theoretical physics. Maldacena's 1997 paper has accumulated more than 20,000 citations. The correspondence has been used to compute properties of strongly coupled quantum systems by translating them into geometric calculations in higher dimensional gravity. It has been used to study the interiors of black holes. It has, by some measures, become the most cited paper in the history of high-energy physics. Maldacena was awarded the Dirac Medal in 2008. What Hawking and Hertog were proposing in 2017 was an extension of this correspondence to cosmology. Not a clean extension, a bold and somewhat speculative one, using machinery that had been developed for a different problem and bending it to address the structure of the multiverse. The technical move was this. The geometry of an inflating universe is, in the relevant approximation, de Sitter space. De Sitter space, like anti-de Sitter, has an asymptotic boundary, a kind of mathematical horizon at the far future of the inflating region. Hawking and Hertog proposed that the wave function of the universe, computed by the no-boundary path integral, could be reformulated as the partition function of a Euclidean conformal field theory living on this asymptotic boundary. Instead of doing the path integral over four-dimensional geometries directly, you could compute the same physical quantity by doing a path integral over three-dimensional field configurations on the boundary. This was not a new idea in isolation. Versions of a de Sitter holographic correspondence, sometimes called DS/CFT, had been floated in the early 2000s by the American physicist Andrew Strominger, then at Harvard, and by several other authors. What was new in the Hawking-Hertog paper was the application of this correspondence to the specific problem of eternal inflation. Eternal inflation, in the standard picture, produces an infinite four-dimensional spacetime with an infinite ensemble of pocket universes embedded inside it. The asymptotic boundary of that spacetime, however, is mathematically much smaller. It is a three-dimensional surface, and the field theory living on this surface, the one whose partition function gives the wave function, has a finite entropy. The entropy of a field theory is, intuitively, a measure of how many distinct configurations the theory can be in. A coin has two configurations and an entropy of 1 bit. A standard playing card deck has about 225 bits. The entropy of a field theory on a continuous surface is, in general, infinite. There are infinitely many ways to vary a continuous field across a surface. But the entropy of a quantum field theory at finite temperature, or on a bounded surface, can be finite and is computable using the standard machinery. The entropy of the boundary theory in the Hawking-Hertog framework, computed using a cosmological version of the Bekenstein-Hawking formula that governs black hole entropy, comes out finite. The exact value depends on the specific cosmological history, but it is bounded above by a quantity related to the area of the de Sitter horizon at the end of inflation. This bound is the key to the smooth exit. The number of distinct cosmological histories the wave function can describe is bounded by the entropy of the boundary theory. If the entropy is finite, the number of histories is finite. If the number of histories is finite, the multiverse is not infinite. The infinite ensemble of pocket universes predicted by eternal inflation in this argument is a mathematical artifact of the bottom-up four-dimensional description. The top-down holographic description, computing the same quantity from the boundary, gives a finite answer. This was the smooth exit. The phrase referred, in the paper itself, to the specific mathematical mechanism by which the inflating spacetime reached its asymptotic boundary. In the standard picture of eternal inflation, the inflating region never ends globally, and the boundary is an idealized object that exists only at infinite future time. In the holographic picture, the boundary is a real object with a well-defined geometry and a well-defined field theory living on it. The transition from the inflating bulk to the asymptotic boundary was the smooth exit. Smooth in the technical sense that the field configurations on the boundary varied continuously, with no discontinuities or singularities. Smooth in the broader sense that the wild, unbounded growth of inflating space in the standard picture was replaced by a clean, finite structure at the boundary. The implication was that eternal inflation, when described holographically, was not actually eternal in any meaningful physical sense. It was a phase of cosmological history that had a well-defined end, captured in the geometry of the asymptotic boundary. The multiverse, far from being infinite, was a finite set of histories indexed by configurations of the boundary field theory. The smooth exit, in other words, did real work. It cured the measure problem. It restored predictivity to inflation. It gave the no-boundary proposal, the project Hawking had been refining for 35 years, a concrete mechanism for producing the kind of finite cosmological ensemble it had always seemed to require. The paper went on to compute, in a simplified model, what some of these boundary field configurations actually looked like. The calculation was preliminary. The full theory was not in hand. What Hawking and Hertog had was a toy model in which the basic features of the argument could be displayed. The toy model was based on a four-dimensional gravity theory coupled to a single scalar field, the inflaton, together with a particular choice of asymptotic boundary conditions. In this toy model, they could show explicitly that the wave function was peaked on a specific, finite class of cosmological histories. The peak corresponded to universes that began with inflation, exited inflation smoothly into a hot Big Bang, and produced the kind of small-scale structure consistent with observation. The peak was sharp. It was not spread, as in the infinite multiverse picture, across every possible kind of universe. It was concentrated on universes that looked, in their broad features, like ours. This was the central technical claim of the paper. The wave function of the universe, computed holographically, predicts a specific, bounded ensemble of histories, rather than an infinite fractal of pocket universes. The smooth exit from eternal inflation is mathematically real. The multiverse, if it exists at all, is finite. The paper put this claim forward as a possibility, not as a proof. The phrase appeared in the abstract, with appropriate hedges. The conclusions were stated as the predictions of a particular framework, not as established facts. The mathematical machinery used was, by the author's own admission, incomplete, a working approximation rather than a finished theory. The paper called for more work, by more researchers, to test whether the result could be made rigorous in the full theory. But the structural argument was there. Between the archive submission in July of 2017 and the revised version uploaded in March of 2018, the paper went through extensive revisions. The collaborators added new sections. They tightened the mathematical arguments. They responded to comments from colleagues who had read the preprint and circulated objections. Hertog has described, in interviews and in his 2023 book, the strange experience of working on these revisions through the autumn and winter of 2017, with Hawking visibly weakening week by week. The pace of work was, even by the standards of their 20-year collaboration, slow. The cheek-twitch interface, by late 2017, was producing perhaps one word every 2 minutes. A single email response from Hawking might take an entire afternoon. The collaborators communicated, increasingly, through facial expressions, with Hertog reading the slight movements of Hawking's brow and lips for indications of agreement or hesitation. The mathematical revisions in this mode became as much an act of interpretation as of dictation. The version uploaded on March 4th incorporated all of these revisions. It contained additional mathematical detail on the holographic argument. It addressed several technical objections that had been raised against the preprint. It strengthened the central claim that the mechanism was, in the toy model, a robust feature rather than an artifact of the particular calculation. Hawking did not see the final acceptance of the paper. He did not see the publication, 6 weeks later, in the Journal of High Energy Physics. He did not see the citations that would accumulate over the next several years as other physicists took up the holographic approach and worked out its implications. He saw the submission. He approved it. Then he ran out of time. The paper, published posthumously on April 27th of 2018, was Hawking's last scientific work. It was also, by most accounts, the most speculative piece he had ever attached his name to. Hawking had spent his career making bold conjectures, but they had usually been conjectures supported by rigorous mathematical demonstrations. This one was different. The argument it made required machinery that did not yet fully exist. The mathematical framework of de Sitter holography was, by 2018, still incomplete and contested. The application of holography to cosmology, while increasingly studied, was nowhere near as mature as the application to anti-de Sitter spacetime. The paper was, in a sense, a research program disguised as a result. This is, perhaps, what Hawking wanted. He had spent the last decades of his life trying to drag the multiverse back inside the reach of testable physics. The paper was, by his own framing, the opening move of a strategy rather than its conclusion. Hertog, in his book, has described it as the kind of work that a younger physicist would have called speculative. Hawking, knowing he had no more time, wanted the speculative claim on the record. The detailed mathematics, the rigorous proofs, the experimental tests, those could be worked out by others. That was the gamble. To plant a flag, in the limited time remaining, in a corner of cosmology where no one had quite planted one before. To suggest that the multiverse was bounded, that the no-boundary proposal extended naturally to a holographic description, that the measure problem could be solved, even if the details would take decades to work out. To leave behind, in the literature, a target for younger physicists to aim at. That target had a name. The name was the smooth exit. Whether it would hold up was, in the spring of 2018, an open question. It still is. The paper that was eventually published on April 27th of 2018 was the product of approximately 18 months of intense, slow collaboration. The first version of the manuscript was assembled in the early summer of 2017 in a back and forth that took place mostly across the English Channel. By that time, Hertog had been a professor at the Catholic University of Leuven for 6 years. He had moved from Cambridge to Belgium in 2011, taking up a position in the theoretical physics department in his native country. He was, by 2017, splitting his time between his teaching responsibilities at Leuven, his ongoing research program, and the visits to Cambridge that were the operational lifeblood of his collaboration with Hawking. The visits had become more frequent as Hawking's condition worsened. By 2017, Hertog was traveling to Cambridge roughly every 2 weeks, staying for 2 or 3 days at a time, working with Hawking in the office at the Department of Applied Mathematics and Theoretical Physics that Hawking had occupied for decades. The office itself was modest. A desk, a wall of books. The motorized wheelchair that Hawking lived in, equipped with the speech synthesizer that had been his only mode of communication for 32 years. A graduate student or two, usually helping with the day-to-day mechanics of Hawking's working life, adjusting the wheelchair, transcribing dictated emails. The window looked out onto a courtyard. There was an old photograph of Newton on one wall and a framed printout of the Hawking radiation formula on another. The office had not changed in any major way in 20 years. It would not change in the year that remained. Working sessions in 2017 typically ran from late morning until early evening, with Hawking dictating revisions through the cheek twitch interface and Hertog reading them off the screen of the laptop attached to the wheelchair. The dictation was slow. By the early summer of 2017, Hawking was producing approximately 1 word every 2 minutes when he was working at his best, and less when he was tired. A single paragraph of mathematical text might take an entire afternoon to compose. A full section of the paper, with its equations, its citations, its careful hedges and qualifications, might take a week of working sessions to dictate. The collaboration had, over the years, developed a particular working style adapted to this pace. Hertog would arrive with a typed draft of a section, prepared in Leuven the previous week. Hawking would read it slowly, considering each line. He would dictate revisions 1 word or 1 phrase at a time. Hertog would type the revisions into the document. When a passage was unclear, or when Hertog suspected he had misunderstood, Hawking would indicate his response through small movements, a raised eyebrow for assent, a held expression for disagreement. Over the years, Hertog had learned to read these signs with reasonable confidence. The pace of explicit dictation through the speech synthesizer was reserved for the moments where the language had to be exact. The pattern of these visits, through the summer and early autumn, was steady. Hertog would arrive in Cambridge on a Monday evening and walk to the office in the morning. The walk took about 15 minutes through the quiet streets near the mathematics campus. He would let himself in, exchange a few words with the graduate students or the staff helping Hawking, and then sit down at the desk across from the wheelchair. The motorized chair would already be in position by the window, with Hawking facing the courtyard. The morning light, when there was morning light, came in from the left. The room held a particular stillness on most working days. There was no fanfare, no sense of urgency from inside it. The clicker, when Hawking used it, made a small mechanical sound, audible only to people sitting very close. Hertog had learned to listen for it. He had learned to read the smaller signs too. The slight tilt of the head, the way Hawking's eyes moved across the screen at one speed when the text was working, and a different speed when it was not. The reading aloud passes through each section of the draft were the slowest part of the day. The dictation was faster in the strict sense, but it required more concentration from both of them. A morning of this kind of work, on a good day, might produce a single new paragraph. On harder days, it produced a few sentences, or consisted entirely of correcting earlier dictation that the speech synthesizer had misregistered. Hertog took breaks every 2 hours, going outside into the courtyard, returning with coffee. The office was quiet except for the faint hum of the wheelchair's electronics and the slow accumulation of words on the laptop screen. By late afternoon, when the light in the courtyard began to fade, Hertog would close the laptop, exchange a few words about the next day's plan, and head out. The next morning would begin the same way. By the autumn of 2017, several things were becoming clear. The paper was almost ready. The archive preprint had been uploaded on July 24th. The first round of feedback from the broader cosmology community had arrived, and most of it was constructive. Hawking and Hertog were working through the comments, deciding which ones required revisions and which ones could be addressed in later work. The plan was to submit a revised version to the Journal of High Energy Physics in early 2018. The other thing that was becoming clear was that Hawking was running out of time. The decline through the autumn was gradual but unmistakable. Hawking's working sessions grew shorter. The intervals between visits from Hertog grew tighter, with Hertog flying to Cambridge increasingly often as the months wore on. The synthesizer, by late 2017, was sometimes registering Hawking's cheek movements imperfectly, and a sentence that should have taken 20 minutes to dictate would sometimes take an hour, as words had to be corrected and recorrected. Hertog has written, in his 2023 book, about the particular kind of patience this required from both of them. Hawking, slow and visibly tired, refusing to abandon a particular formulation he wanted in a particular sentence. Hertog, watching him, knowing what the slowness meant. The revisions to the paper through autumn and winter focused on two areas. The first was the technical justification of the DS/CFT correspondence in the toy model, including how the bounded ensemble of histories related to specific observational features such as the cosmological constant and the spectrum of cosmic microwave background fluctuations. Several critics of the preprint had pointed out that the holographic argument required steps that were not, by the standards of theoretical physics, fully derived. Hawking and Hertog tightened these steps. They added several pages of mathematical detail in the appendices, showing more explicitly how the partition function of the boundary theory connected to the wave function of the bulk geometry. The second area of revision was the discussion of what could be tested. Hawking, in the final months, was particularly insistent that the paper include a clear statement of the framework's testable predictions. He did not want the paper to be read as untestable speculation. He wanted future cosmologists to know what experiments would, in principle, distinguish the smooth exit framework from its competitors. The revised version was completed in late February of 2018. The collaborators went through it one more time, line by line, in a series of working sessions during the first 3 days of March. Hawking, by this point, was visibly fragile. Hertog has described the sessions as quiet, focused, almost monastic in their slowness. There was no urgency in Hawking's manner, even though both men understood the urgency of the situation. There was only the work. On March 4th, the revised paper was uploaded as a preprint to the archive. Hertog handled the upload. Hawking signed off on the final version with a series of slow cheek clicks confirming each section. The file went up from a computer in the Cambridge office in the late morning. Hertog flew back to Belgium the next morning. 10 days later, on March 14th, Hawking died at his home in Cambridge. Hertog received the news in Leuven by phone. He flew to Cambridge that evening. There were arrangements to be made and colleagues to inform. The paper, still under peer review, sat in the queue at the journal, working its way through the editorial process. The review came back in early April, with minor revisions requested. Hertog made the revisions alone. The paper was accepted on April 20th and published on April 27th. That sequence, the archive upload on March 4th, the death on March 14th, the acceptance on April 20th, the publication on April 27th, is the actual chronology of Hawking's last published work. The headlines that followed the publication, the ones that claimed Hawking had proven the multiverse exists, were almost entirely written by science journalists who had not yet read the paper. What Hawking had actually done in those last working sessions was something quieter and more characteristic. He had insisted on putting a specific, falsifiable, mathematically articulated alternative to the infinite multiverse on the record. He had insisted on doing this with the precision he had spent his whole career trying to achieve. He had used the last working months of his life to ensure that the question he had been thinking about for 40 years was, on the record, in a form that other physicists could pick up and pursue. The paper was, in that sense, his final argument. Not a proof, not a conclusion, an argument. One more move in a conversation he had been having with the cosmology community for half a century, and one that he wanted to make sure was on the table when he was no longer there to make it. The conversation he had been having was a quiet one. It had not, for most of his career, been a public one. Hawking's public profile had been built on other things, on Hawking radiation, on a brief history of time, on his appearances on television and in popular culture as the world's most recognizable theoretical physicist. The deep work he had been doing throughout was on the no-boundary proposal and its extensions. The smooth exit paper was the culmination of that quiet line. It was the line of work that he, more than anyone else, had defined and pursued. And it was the line of work that, when he was no longer there, would have to be carried forward by Hertog and by the small community of physicists who had been paying attention to what Hawking was actually doing for the last 20 years of his life. That community would do what it could. Whether it would be enough was, in the spring of 2018, the open question. If the paper's central claim is correct, almost everything cosmology has been trying to do with the multiverse for the past 40 years needs to be reconsidered. Start with the anthropic principle, the argument that had quietly become the working explanation for the apparent fine-tuning of the physical constants. The argument depended in its strongest form on the multiverse being infinite. The reason was straightforward. The fine-tuning of the cosmological constant, of the particle masses, of the strength of the nuclear forces, is so extreme that any individual universe drawn at random from the space of possibilities would, with overwhelming probability, fail to host observers. The anthropic principle handles this by pointing out that we observe a universe with friendly constants because we could not have observed any other. But to make the argument do real work, to turn it from a tautology into an explanation, you need the friendly universes to actually exist somewhere. You need a large enough ensemble of universes that the friendly ones are statistically guaranteed to appear, even if they are vanishingly rare. An infinite ensemble does this trivially. A finite ensemble of bounded size may not. If the smooth exit framework is right, the ensemble is finite. The anthropic explanation does not automatically disappear, but it has to do more work. You can no longer say, lazily, that any conceivable universe exists in some pocket of the multiverse, and we just happen to be in one of the friendly ones. You have to ask whether the specific finite ensemble that the no-boundary proposal selects actually contains friendly universes in sufficient number to make our existence statistically unsurprising. That is a much more constrained question, and it is, in principle, computable. Hawking and Hertog argued that the finite ensemble selected by the holographic no-boundary proposal does, in fact, contain a healthy population of universes with parameters in the range that allows for stars and galaxies and chemistry. The argument is not that fine-tuning is irrelevant. The argument is that the fine-tuning required to be in the friendly part of the ensemble is much weaker than the fine-tuning required to be in the friendly part of an unconstrained infinite multiverse. Top-down cosmology in this picture doesn't eliminate the puzzle of fine-tuning. It compresses it. It turns a fantastic coincidence into a milder one by showing that the no-boundary proposal naturally selects histories in a relatively narrow band of cosmological parameter space. That compression is the kind of thing physics is supposed to do. A good theory takes phenomena that look miraculous and shows that they are the natural output of a simpler underlying structure. If the smooth exit argument holds up, fine-tuning is not a sign that the universe was made specifically for us. It is a sign that the no-boundary proposal, applied holographically, picks out universes within a particular structural envelope, and our universe sits well inside that envelope. This was, by Hawking's lights, the more honest answer. The picture has another consequence that is, depending on your taste in cosmology, either elegant or unsettling. If the multiverse is finite, with histories selected by a holographic no-boundary state, then the physical laws of any given universe are not eternal Platonic structures. They are themselves products of cosmic history. They emerge along with the universe they govern. Hertog has been pushing this claim hard since Hawking's death. The framing he uses in his 2023 book, On the Origin of Time, is that physics has been doing cosmology backwards for centuries. The standard approach assumes that the laws of physics are fixed, eternal, and somehow logically prior to the universe. The universe is born inside the laws. The laws shape it. The laws stand outside it, unchanging. Hertog argues that the no-boundary picture inverts this. The laws of physics, in their full specificity, the precise value of the cosmological constant, the precise spectrum of particle masses, the precise structure of the fundamental forces, are not given to the universe from outside. They are products of the early universe itself. They condense out of a more primitive, more symmetric state during the no-boundary phase, in the same way that the symmetries of a snowflake condense out of the more symmetric state of liquid water as it freezes. This is, by any honest description, a deeply weird idea. It says that the laws of physics have a history. It says that asking, why is the cosmological constant the value it is, in the deep sense, a question about how the early universe evolved, not a question about external mathematical necessity. The laws of physics, in this framing, are more like biological species than like Platonic forms. They are the result of a kind of cosmic selection process, with the no-boundary proposal acting as the deep filter that determines which laws can emerge. Hertog calls this a Darwinian view of physics. The phrase is provocative. It is meant to be. The traditional self-image of theoretical physics has been one of discovering eternal truths, of uncovering the timeless mathematical structure of reality. Top-down cosmology, taken seriously, suggests this self-image is wrong. The mathematical structures we discover at the level of fundamental physics are themselves contingent. They depend on which history the universe ended up in. There is no view from outside the universe, no Platonic mathematics that exists independently of the cosmos. There is only the universe and the laws that emerged with it. If you find this disorienting, you are not alone. Plenty of working physicists find it disorienting too. The Hertog framing is, even among advocates of the top-down approach, more aggressive than most. Hartley has tended to describe the proposal in more conservative terms as a refinement of standard quantum cosmology rather than a radical reframing of what physical laws are. Hawking, in his last papers, was somewhere in between. He clearly believed the no-boundary proposal extended naturally to a top-down view in which the laws of physics were determined by the cosmic history, but he was less inclined than Hertog to call this a Darwinian revolution. He wanted the mathematics first. The philosophical implications could be sorted out afterward. There is one other strand to all of this that deserves attention, because it turns the top-down approach from pure speculation into something that might actually be tested. The strand is primordial gravitational waves. Inflation, in any of its forms, predicts that the violent stretching of space during the inflationary epoch produces a background of gravitational waves at very long wavelengths. These primordial gravitational waves have a characteristic spectrum. Different versions of inflation predict different spectra. Eternal inflation in the standard infinite multiverse picture predicts a particular kind of spectrum, with certain features at the longest accessible wavelengths. Top-down inflation in the smooth exit framework predicts a different kind of spectrum, with the longest wavelength features shaped by the finite, no-boundary ensemble, rather than by an infinite, eternally inflating background. These primordial gravitational waves have not yet been observed. The leading experimental program designed to detect them is the Laser Interferometer Space Antenna, abbreviated LISA, a planned space-based gravitational wave detector consisting of 3 satellites flying in a triangular formation separated by 2.5 million kilometers, with laser interferometers measuring the tiny changes in distance between them caused by passing gravitational waves. LISA is being built by the European Space Agency in collaboration with NASA. The launch is scheduled for the mid-2030s, with full science operations expected to begin around 2036. When LISA flies, it will be sensitive to gravitational waves at frequencies that correspond roughly to wavelengths comparable to the scale of the inner solar system. This is not directly the frequency of primordial inflationary gravitational waves, which sit at much longer wavelengths, but LISA, together with future ground-based detectors and with continuing observations of the cosmic microwave background, will provide a much more detailed picture of the gravitational wave background of the universe than is currently available. The full program of testing top-down cosmology against eternal inflation through gravitational wave observations is, at the moment, a long-term research effort. The first results that bear directly on the smooth exit prediction may not arrive for another 15 or 20 years. It helps at this point to slow down and describe what these waves actually are. They are ripples in the geometry of space-time, left over from the moment of inflation itself. They were stretched, along with everything else inside the inflating region, until their wavelengths became larger than any object in the universe today. Some of them are the size of galaxies, others are larger still. The longest of them, in principle, span the entire observable cosmos. They are extraordinarily faint. They were generated by quantum fluctuations of the gravitational field during inflation, then amplified to classical strengths by the same exponential expansion that smoothed out the rest of the universe. The cosmos cooled. The waves kept going. Today they form a kind of background noise in the geometry of space itself. They are everywhere. They pass through you, through the Earth, through every star in the night sky, and the entire planet ripples slightly in response, by a distance smaller than a single atomic nucleus. The differences between the two competing spectra are concrete enough to describe. Eternal inflation in the standard picture predicts that the spectrum of waves continues smoothly to arbitrarily long wavelengths. There is no natural cutoff. The inflating region produces gravitational waves on every scale, including scales larger than anything we can ever observe. The smooth exit framework predicts something different. Because the no-boundary geometry has a finite asymptotic surface, the spectrum has a natural cutoff at the wavelength corresponding to that surface. The waves do not continue forever. They are bounded above by a scale set by the geometry itself. The trouble is that the longest wavelength gravitational waves are also the hardest to detect. LISA will measure waves with wavelengths of a few astronomical units, which is enormous by any everyday standard, but small compared to the wavelengths the smooth exit cutoff would affect. For those, the only available detector is the cosmic microwave background itself. The The CMB is the oldest light in the universe, released about 380,000 years after the Big Bang, when the cosmos cooled enough for atoms to form and photons to travel freely. The same primordial gravitational waves that Lisa hopes to detect directly leave a subtle imprint on this radiation. They twist the polarization of the CMB photons into a particular swirling pattern called a B-mode polarization that no other process in standard cosmology can produce. Several experiments are looking for this pattern. The BICEP and Keck telescopes at the South Pole have been refining their sensitivity for over a decade. The Simons Observatory in the Atacama Desert in Chile, beginning operations in the mid-2020s, will measure the polarization of the CMB across thousands of square degrees of sky. The CMB S4 experiment, a network of telescopes scheduled for the late 2020s, will push that sensitivity an order of magnitude further. And Lightbird, a Japanese space mission planned for the early 2030s, will measure the polarization across the entire sky from above the atmosphere. None of these experiments has yet succeeded. There was, in 2014, a celebrated false alarm. The BICEP team announced a detection that turned out, on closer examination, to be galactic dust mimicking the cosmological signal at the wavelengths and polarization angles of interest. The episode was instructive about how hard this measurement is. The signal, if it is there at all, is buried under foreground emission from the dust and magnetic fields of our own galaxy, and the experiments spend most of their analysis effort on cleaning up that contamination. The false alarm was, in the long view, useful. It forced the cosmology community to develop more careful methods for separating cosmic signals from galactic foregrounds, and it tempered the rush to announce future detections. Every subsequent experiment has been built with the BICEP lesson in mind. The standards for what counts as a believable detection of primordial gravitational waves are now extraordinarily high. A real claim, when it comes, will need to survive cross-checks at multiple frequency bands and from independent analysis pipelines before the field accepts it. The expected timescale for a definitive detection, by the more optimistic estimates of the cosmologists involved, is the early 2030s. If a detection is made, the spectrum of the signal will distinguish between competing models of inflation. The smooth exit framework will either match the data or be ruled out. It will not be ruled out by armchair philosophy. It will be ruled out, if it is ruled out at all, by careful measurements of the polarization of a 13.8 billion-year-old light made by telescopes in the Atacama Desert and in low Earth orbit, with their data reduced by graduate students working through the night in offices around the world. Hertog has been organizing this program from his position at the Catholic University of Leuven since Hawking's death. He has been giving talks. He has been writing technical papers. He has been arguing, in interviews and in his book, that the next decade or two of gravitational wave observations will provide the first real test of the no-boundary proposal as a cosmological theory. If the predictions of the top-down approach match what Lisa and its successors measure, the smooth exit framework will move from speculation into the realm of confirmed cosmology. If they don't, the framework will need to be revised or abandoned. This is the standard scientific way of saying that the theory has consequences. It can be wrong. The wrongness, if it comes, will be visible in the data. That, by the standards of modern cosmology, is the highest form of seriousness a speculative idea can aspire to. The community response since the paper's publication in 2018 has been mixed. Some cosmologists have taken up the holographic no-boundary program enthusiastically, publishing follow-up papers that extend the framework, refine the calculations, and explore its observational consequences. Hertog's own group at Leuven has been one center of this activity. The broader community of researchers working on quantum cosmology, on holographic methods, on the foundations of inflation, has divided itself, roughly, between those who see the Hawking-Hertog argument as a promising new direction and those who see it as a speculative overreach that has not yet earned its place at the table. The numbers, by mid-2026, are still modest. The smooth exit paper itself has been cited several hundred times. That is a respectable number for a cosmology paper, but it is not by the standards of the field, a citation pattern that suggests the framework has been universally adopted. Compare it, for instance, with Maldaceni's 1997 AD/CFT paper, which has accumulated more than 20,000 citations. The Hawking-Hertog paper is more like a quiet bet on a particular research direction than like a community-wide consensus. That is, by Hertog's own account, what Hawking expected. He did not expect the smooth exit paper to be the last word on eternal inflation. He expected it to be the first word in a long conversation. The conversation has been ongoing for the past 8 years, with both supporters and critics adding new arguments, new calculations, and new objections to the literature. The state of the field, as of this recording, is one in which the holographic, no-boundary approach is taken seriously by a working minority of cosmologists and viewed skeptically by a larger working majority. This is not a comfortable place for a theory to live. It is the place where many theories die. It is also the place where some theories survive long enough to become standard cosmology. Inflation itself lived in this awkward zone for most of the 1980s. The Maldacena correspondence lived in it for most of the late 90s. The pattern in modern theoretical physics is that ambitious ideas spend a decade or two in a contested middle space before either the experimental evidence or the accumulation of internal coherence pushes them into the mainstream, or before the lack of either pushes them into obscurity. Which way the smooth exit framework will go is, at this point, genuinely unknown. The mathematical arguments are not finished. The experimental tests are decades away. The community has not yet made up its mind. Hertog is still working on it. Other groups are still working against it. Hawking is no longer working on anything. There is a separate set of objections to the framework that are worth pulling out and looking at directly, because they go to a different kind of question than the technical questions about whether the math actually works. The technical objections, the ones from working cosmologists, mostly concern whether the holographic argument is rigorous enough to bear the weight that Hawking and Hertog placed on it. The deeper objections, the ones that have come from outside the immediate quantum cosmology community, concern whether the project of trying to predict the multiverse from inside it is a coherent scientific project at all. That is the question we want to walk into next. The deeper objection to the smooth exit framework, the one that has come from outside the immediate quantum cosmology community, runs through a Viennese philosopher of science who died in 1994. His name was Karl Popper. He published his most influential book, The Logic of Scientific Discovery, in 1934, and he spent most of the next 60 years arguing that the central question in the philosophy of science is what distinguishes scientific claims from non-scientific ones. Popper's answer, sharpened over decades of argument with other philosophers, was that scientific claims are claims that could, in principle, be shown to be false. A claim is scientific, not because it has been proven true, but because it makes predictions that could fail. The more daring the predictions, the more falsifiable the claim, the more scientific it is. Popper's criterion has been controversial among philosophers of science for almost as long as it has existed. Many working philosophers think it is too strict, that science is messier than Popper's clean falsificationism allows. But the criterion has remained powerful as a rough and ready way of asking whether a particular research program is doing science or doing something else. And the criterion has been pointed repeatedly at multiverse cosmology. The phrase falsificationism carries some baggage among working philosophers, but Popper himself had reasons for caring about the question that went beyond philosophical fashion. He had been born in Vienna in 1902 into an assimilated Jewish family that prized intellectual culture. He had come of age in the city's interwar period, when Vienna was one of the most intellectually fertile cities in the world, home to the logical positivists of the Vienna Circle, to the early development of psychoanalysis, to the foundations of modern economics, and to the philosophical work of the young Ludwig Wittgenstein, who was making his way through the same university circles a decade ahead of Popper. Popper had absorbed all of this. He had also watched, with mounting alarm, the rise of intellectual movements that claimed the certainty of physics, but lacked the structure to be wrong about anything. Freudian psychoanalysis and Marxist historicism were his two favorite examples. Both, in Popper's view, had a particular pattern. They could explain anything. Any observation could be fit after the fact into the theory. Any failed prediction could be reinterpreted as a confirmation. Any apparent counterexample could be absorbed by an additional layer of interpretation. This, in Popper's view, was not science. It was something else. A sophisticated narrative apparatus capable of generating plausible explanations indefinitely, but incapable of being wrong. Popper fled Vienna in 1937, about a year before the German annexation of Austria. His Jewish background, combined with his outspoken criticism of the totalitarian movements then on the rise across Europe, made staying in the city dangerous. He spent the war years in New Zealand, teaching at Canterbury University College in Christchurch. He wrote during that period his most important political work, a 2-volume defense of liberal democracy titled The Open Society and Its Enemies, published in 1945. After the war, he was offered a position at the London School of Economics, where he taught for the next 23 years until his retirement. The falsificationism criterion was developed across this whole period, but it remained throughout anchored to that early Viennese experience. The experience of watching plausible-sounding theories that could not, by their own internal structure, be tested against the world. The experience of intellectual movements that explained too much and that turned with frightening ease into political movements that justified anything. The multiverse, in this lineage, is exactly the kind of thing Popper would have worried about. It can accommodate any observation. It explains everything by allowing every possible universe to exist somewhere in the ensemble. The infinite multiverse, in Popper's framework, is a sophisticated narrative apparatus rather than a scientific theory. The comparison is not perfect, of course. The multiverse is not a political movement, and the physicists who advocate for it are not, by any reasonable measure, doing what Freud or Marx were doing. They are doing serious mathematical work. But the structural objection is the same. A theory that explains everything in principle has no traction on what the world actually is. The world could be otherwise, and the theory would still explain it. The world could be exactly the way it is, and the theory would not have predicted that specifically. The theory is, in the Popperian sense, frictionless. The Popperian objection runs like this. The multiverse, in the standard infinite fractal eternal inflation picture, makes no predictions that can be falsified. Every conceivable observation is consistent with some pocket universe in the multiverse, and our particular observations are filtered by the anthropic principle to be consistent with our particular pocket. The theory cannot be wrong about anything. Anything we see can be accommodated. Anything we don't see can be attributed to being in a different pocket. The multiverse, as a scientific hypothesis, has no teeth. This was, broadly, the criticism Hawking and Hertog were trying to answer. The smooth exit framework was, in part, a response to the Popperian challenge. The argument was that a top-down holographic version of cosmology produces a bounded ensemble of histories, and a bounded ensemble makes predictions. The predictions are about the statistical properties of cosmic structures, about the spectrum of primordial gravitational waves, about the relationships between cosmological parameters that are independently measurable. These predictions could, in principle, be wrong. If they were wrong, the framework would be in trouble. The theory has teeth. Whether the teeth bite hard enough to actually constitute science, in the Popperian sense, is what the critics have been arguing about. One of the more pointed early reactions came from Frank Wilczek, a theoretical physicist at MIT, who won the Nobel Prize in 2004 for his work on the strong nuclear force. Wilczek, asked about the Hawking-Hertog paper shortly after its publication, called it heavy on speculative assumptions. He was not dismissing the paper. Wilczek has himself worked on speculative cosmology and is, on the whole, sympathetic to ambitious theoretical projects. The criticism was specific. The mathematical machinery the paper relied on, the de Sitter holographic correspondence, and the path integral techniques that connected the no-boundary proposal to its holographic partition function, was, in Wilczek's view, not yet established at the level that would justify the broad claims the paper was making. Wilczek's point was that the paper layered speculation on speculation. Each individual layer might eventually be vindicated, but the cumulative speculation, taken as a whole, made the central claim look more solid than it actually was. A reader encountering the smooth exit argument might come away thinking that the multiverse had been bounded by rigorous mathematics. The reality, Wilczek argued, was that the multiverse had been bounded by a chain of plausible conjectures, each of which was itself the subject of active research. The conjectures might all be right, or some of them might be wrong. The paper did not, in his view, give the reader enough information to tell. This is a sharp criticism. It is the kind of criticism that is hard to answer in the short term, because the only way to answer it is to do the additional research that resolves each of the underlying conjectures. Hertog's program since Hawking's death has been, in part, exactly this kind of follow-up work. Whether it will succeed in turning the smooth exit framework from a chain of conjectures into a chain of theorems is, in 2026, an open question. A different kind of criticism came from Sabine Hossenfelder, a German physicist who has written extensively on the foundations of modern cosmology and on what she sees as the field's drift away from empirical accountability. Hossenfelder's reaction to the Hawking-Hertog paper, expressed in blog posts and interviews around the time of its publication, was sharper than Wilczek's. She called the paper utterly unremarkable. The argument it made, in her view, was not new in any important sense. The holographic approach to cosmology had been discussed since the early 2000s. The application to eternal inflation was an incremental step, not a breakthrough. The paper's prominence, Hossenfelder suggested, came from the timing, its association with Hawking's death, rather than from any substantive scientific contribution. This criticism is harder to evaluate. It is a sociological claim as much as a scientific one. Hossenfelder is arguing that the paper was overhyped because of who wrote it and when, not because of what it said. The question of whether the paper would have received the same attention if it had been written by two unknown postdocs is impossible to answer in a controlled way. The paper exists in the form it does. With the author it has. We cannot replay history with the author removed. What we can do is read the paper on its merits and ask whether the central technical claim is interesting independent of the biographical circumstances. The claim that holographic methods bound the entropy of eternal inflation and that this bound implies a finite multiverse is a substantive claim. Whether it is interesting enough to warrant the attention it has received is a question that working cosmologists can legitimately disagree about. Hossenfelder's view is that it is not. Other working cosmologists, including Hertog's collaborators at Leuven and elsewhere, take a different view. There is one specific quotation from Hawking himself, given in interviews around the time of the paper's submission, that has been cited frequently in discussions of the smooth exit framework. The quotation runs as follows: "We predict that our universe, on the largest scales, is reasonably smooth and globally finite. So it is not a fractal structure. This is, on its surface, a calm scientific statement. It says, here is what our theory predicts, and here is what it does not. The universe is not an infinite fractal of bubble universes with wildly varying physics. It is, on the largest scales, a finite and reasonably smooth thing. This is a prediction. If observations show that the universe is, on the largest scales, fractally structured with wildly varying properties, the theory is wrong. The problem is that observations cannot directly probe the universe on the largest scales. The largest scale we can observe is the size of the cosmological horizon, the boundary beyond which light has not had time to reach us in the lifetime of the universe. Anything beyond that is, by construction, unobservable. The claim that the universe is globally finite is a claim about regions of space-time we cannot see. The theory predicts global properties. The observations can probe only local properties. The Hawking quotation deserves a closer look because the specific words he used in that interview were carefully chosen. Hawking did not say that the universe is finite. He said that it is reasonably smooth and globally finite. The word reasonably is doing real work in that sentence. It does not say the universe is perfectly smooth. It does not say there are no variations from one large region to another. It says that the variations are bounded, that they do not run away into the wild fractal structure that eternal inflation predicts in its standard form. This matters for testability because it tells us what kind of observation could disprove the framework. If the observable universe shows on its largest measurable scales the kind of wild variation that an eternal inflation multiverse predicts, large patches with different effective physics, sharp transitions between regions, statistical properties that vary depending on where in the sky we look, the smooth exit framework is in trouble. We have not seen this. The cosmic microwave background, measured by the Planck satellite across the entire sky to a precision of 1 part in 100,000, looks remarkably uniform. The large-scale distribution of galaxies, mapped by surveys like the Sloan Digital Sky Survey and the Dark Energy Survey, looks uniform in the relevant statistical sense. So far, every measurement we have made of the universe on the largest accessible scales is consistent with what Hawking called reasonable smoothness and global finiteness. This is not, of course, a confirmation of the smooth exit framework. The same data is consistent with the standard single-field inflation picture, with no eternal inflation at all. The data is also consistent with various alternative cosmological models. What the data does is narrow the space of viable theories. It rules out the most aggressive versions of eternal inflation. It is, in a Popperian sense, the beginning of falsifiability rather than its completion. The framework has not been falsified, it has also not been confirmed. The strict Popperian would say that what is happening slowly and incrementally over the next 2 decades of observational cosmology is the process by which a speculative, theoretical proposal earns or loses the right to be called scientific. This is not by itself a fatal problem. Many scientific theories make claims about regions we cannot directly observe, and we evaluate those claims by looking at their consequences for things we can observe. The smooth exit framework predicts specific patterns in the cosmic microwave background, specific spectra of primordial gravitational waves, specific relationships between observable cosmological parameters. If those predictions are confirmed, the global claim about finiteness gains credibility, even if the global claim itself is not directly testable. But the link between the local predictions and the global claim is the thing that is doing the work. And the link, as Wilczek pointed out, depends on a chain of speculative assumptions about holography, about the no-boundary proposal, about the connection between asymptotic field theory and bulk geometry. Each link in the chain can be questioned. The chain as a whole, even if every link is plausible, is not as robust as a single direct prediction. This is the actual situation. It is more interesting in a way than the simple narrative the early headlines about the paper suggested. The paper did not prove the multiverse exists. The paper did not disprove the multiverse. The paper made a specific technical claim supported by a chain of mathematical arguments, each of which is contested and each of which connects to broader research programs that are themselves still ongoing. The smooth exit framework is a piece of unfinished business. It will either move toward completion or be set aside as more people work on it. What is perhaps unsettling about all this is not the technical content, but the timing. The standard read of the headlines after Hawking's death was that the paper showed the multiverse was real. The actual content of the paper, when read carefully, showed something close to the opposite, that the infinite multiverse predicted by eternal inflation was probably wrong, and that a finite, bounded multiverse selected by the no-boundary proposal might be right instead. The gap between what the paper said and what the headlines reported was wide. The reason for the gap is, partly, the structure of science journalism, which simplifies. The reason is also, partly, what Hawking himself chose to do in the final months of his life. He chose to put a speculative paper, on a contested topic, on the record. He chose to do this knowing he would not be around to defend it or refine it in response to critics. He chose, in other words, to spend his last working months on a question he had been trying to settle for 35 years and knew he would not finish. That is what is actually unsettling about the smooth exit paper. Not that it claims the multiverse is real, not that the math is contested. The unsettling thing is the deathbed urgency of a working physicist trying, in the few weeks he had left, to get a particular speculative claim into the literature. The unsettling thing is the precision with which Hawking timed the submission of the revised version, March 4th, 10 days before he died, and the precision with which the rest of the world failed to notice what he was trying to say. The smooth exit paper is not the work of a man trying to settle a question. It is the work of a man trying to keep a question alive. Hawking died on March 14th, 2018. He was 76 years old. He had been diagnosed with motor neurone disease at 21 and given 2 years to live. He had outlived that prognosis by 53 years. The death itself was peaceful. He was at his home in Cambridge. His 3 children were present. The cause of death was given as complications from the disease he had lived with for 55 years. There was no medical drama. The body, by that point, had been a long time arriving at the place where it could finally rest. He was buried in Westminster Abbey on June 15th, in a ceremony at which his ashes were interred near the graves of Isaac Newton and Charles Darwin. Newton and Darwin had each, in their own way, redrawn the human understanding of the cosmos. The placement of Hawking's remains between them was, by the design of the Abbey, a statement about how the British scientific establishment wished him to be remembered. He had taken on the largest questions in physics, pushing against the limits of what theoretical cosmology could say. He belonged, the placement claimed, in that company. The memorial stone in the Abbey bears his most famous equation, the formula for the temperature of a black hole. The inscription itself is in English, translating the Latin words on Newton's nearby gravestone. It does not mention the smooth exit paper. The paper was, at the time of the burial, not yet published. The world that came to Westminster Abbey to remember Stephen Hawking did not know what he had been working on in the final weeks of his life. The paper appeared in print on April the 27th. The first wave of citations began that summer. By the end of 2018, the paper had been cited several dozen times. By the time of this recording, in 2026, the citation count sits in the low to mid-hundreds. The number is, by the standards of high-energy physics, respectable. It is not, by the standards of Stephen Hawking, large. This is the part of the story that does not get told often. The paper is not, by raw influence, one of Hawking's major contributions to physics. His 1975 paper on Hawking radiation, the calculation that showed black holes emit thermal radiation and slowly evaporate, has been cited more than 10,000 times. His 1983 paper with Hartley on the no-boundary proposal has been cited more than 6,000 times. The paper from March of 2018 is, in the long shadow of his career, a minor work, a speculative footnote in the citation record to a body of foundational results. But it is, for the rest of us, the part of his work that bears most directly on the experience of being alive at the edge of one's own time. It is the document of a working scientist refusing, in his final weeks, to leave a question alone. It is the record of an attempt to keep an argument going past the point at which the arguer would be around to make it. There is a phrase I keep returning to. The phrase is the smooth exit. In the paper, it referred to a particular mathematical mechanism by which an inflating universe reaches its asymptotic boundary. In the months I have spent thinking about this story, the phrase has come to mean something else as well. The smooth exit was the universe's. It was also Hawking's. The same mathematical structure that, in Hawking's argument, bounded the wild infinity of eternal inflation also bounded, in a quieter way, the life of the man making the argument. Both exits were finite. Both were, in their way, smooth. The universe, in this framework, does not run on forever. It has a bounded structure. The histories that the no-boundary proposal selects are finite in number. The cosmological boundary is a real object with a real geometry. The infinite multiverse is replaced by a finite, well-defined ensemble. The universe, properly understood, has an end at the boundary. Hawking ended at his own boundary. The boundary was March 14th, 2018. The geometry of his life, from 21 to 76, was a particular trajectory through a particular configuration space. The configuration space, in the broadest sense, was the same one the rest of us inhabit. The trajectory was unique. The boundary was, like all such boundaries, abrupt and not abrupt at the same time. There was a long approach. There was a final 10 days during which he was working on the revisions. There was the submission. There was the death. The submission and the death were, in the order in which they occurred, separated by 10 days. In the order in which they reached the world, they were separated by 6 weeks. Hawking died first. The paper appeared after. The citations began arriving after that, accumulating slowly over the following years, each one a small response by some other working physicist to the question Hawking had not lived long enough to settle. If you have been listening to this for the past 2 hours, you are now somewhere in the late hours of your evening or the early hours of your morning. The room is quiet. The light is low. There is a particular quality to this kind of attention that I want to acknowledge before I close. You've been thinking with me about a man who spent the last decades of his life trying to drag the largest possible questions back inside the boundaries of testable science. That is a particular kind of company to keep at this hour. The office in Cambridge sat empty for several weeks after the death. The graduate students who had helped with the day-to-day mechanics of Hawking's working life moved their things to other offices. The wheelchair was put into storage. The synthesizer was archived. The desk was cleaned. By midsummer, the office had been reassigned to another researcher. The transition happened, in the way these transitions usually happen at universities, with minimal ceremony and considerable practical efficiency. Hertog has written about a particular afternoon in late April, after the funeral but before the publication of the paper, when he went back to the office one more time to retrieve some of his own notes. The room was almost empty. The books were still on the shelves. The papers on the desk were arranged the way Hawking had liked them. Hertog stood in the doorway for a few minutes before going in. He was 42 years old. He had been working with Hawking for 20 years, since the summer afternoon when he had walked into the same office as a 23-year-old graduate student, and Hawking had told him that the universe appeared designed. The next stage of the work, whatever it was going to be, would not have Hawking in it. The published paper went to journals and libraries all over the world. The first wave of citations began arriving over the following months. Hertog continued the program. The smooth exit framework, as a research direction, continued to develop. The community of cosmologists working on the holographic approach to cosmology, which had been a small and somewhat marginal group before 2017, grew slowly through the late 2010s and early 2020s. There are, as of this recording, several dozen physicists actively working on follow-up problems suggested by the Hawking-Hertog paper. They publish technical papers. They train graduate students. They give talks at conferences in Cambridge and Princeton and Santa Barbara. The work continues. Hawking would, by all accounts, have been pleased by this. He had spent his life trying to keep a particular kind of question alive. The question of how to apply the principles of quantum mechanics rigorously to the universe as a whole. He had not solved the question. He had, by his own assessment in his last years, made some progress on it. The progress was incomplete. The future of the program depended on younger physicists picking it up and pushing it further. That, in the end, is what scientific work is: a long conversation across generations. Each contributor adds what they can in the time they have and trusts the next contributors to take the work further. Newton had done this. Darwin had done this. Hawking, buried between them in Westminster Abbey, had done this. The smooth exit paper was his last contribution to the conversation. The contributors who came after, Hertog at Leuven and the wider community at Cambridge and elsewhere, are still working on it. The conversation has not ended. There is something quietly hopeful in this, even at the end of a long story about a dying scientist racing to get one more paper into the literature. The story is not a tragedy. The story is, at most, a particular kind of bittersweet. Hawking ran out of time. He knew he was running out of time. He used the time he had on the question he most wanted to leave on the table. The question is on the table. Other people are now working on it. That is the maximum any scientist working at the edge of what is currently knowable can hope to achieve. The questions Hawking was working on are, in the technical sense, unsettled. The framework may turn out to be right. It may turn out to be wrong. The next 2 decades of gravitational wave observations may move it decisively in one direction or the other. The community of working cosmologists may converge on the holographic no-boundary picture as the standard model of the early universe, or it may move on to a different framework entirely. We do not know. What we know is what Hawking did with the time he had. He spent 55 years thinking about cosmology after being told he had 2. He spent the final 20 of those years building a framework in which the multiverse was finite. He spent the final months of his life pushing one more paper into the literature on this subject. He died 10 days after submitting the revisions. The paper was published 6 weeks later. That sequence of events is the actual content of the headline that, when he died, was reported around the world as Stephen Hawking's final paper proves the multiverse exists. The headline was wrong in every important way. The paper did not prove the multiverse exists. It argued that the standard infinite multiverse, the one cosmology had been comfortable with for 40 years, is probably not what the universe is actually doing. The multiverse, in the paper's argument, is finite, bounded, reachable by the right kind of mathematics from inside. This is what Hawking spent his final days insisting on. Not that the universe is small, not that everything is figured out, only that infinity, as a working assumption, is harder to defend than the cosmology community had assumed, and that there exists at least one mathematically coherent alternative in which the cosmos is finite, even if its boundaries lie far beyond anything we can ever see. I leave you with the question he left for the rest of us. If the universe is finite, what does that change about your relationship to it? If there is no infinite ensemble in which every possible version of you exists, is the version that is listening to this, now, in the quiet hours of your night, more rare than you had been told? The questions are not answerable. They were not answerable when Hawking submitted his final paper. They will not be answerable when the next generation of cosmologists takes up the question and pushes it further into the literature. The point of the questions at this hour is not that they have answers. The point is that someone, in the last weeks of his life, thought they were worth asking.